Hello my viewers. Today I'll be explaining second order differential equation with a constant coefficient. So, as written on the board, we have a second order differential equation labeled as equation 1, where A, B, and C are real numbers. Now, for you to solve this second order differential equation, we need to use a quadratic equation to get the roots of that equation. And after getting the roots, now from this equation 1, we are able to what? To derive this, where our second order differential equation here is denoted as what? R squared. And for this y prime, we have just r, where the last is referred to as a constant. Now, after getting this, let me label it as equation 2. Then we solve this quadratic equation. Now, the root of this equation will determine the general solution of this second order differential equation. And to determine the general solution of this quadratic equation, it involves 3 different cases. Case 1 is when the roots R1 and R2 are real. When they are real, what I'm trying to say here is when R1 and R2 are real, we mean R1 is not equal to R2. For instance, if you solve a quadratic equation whereby your R1 is equal to 3 and your R2 equals to maybe 5 or 2 or any number. So when you have this, R1 is not equal to R2. So in that case, this will be our general solution, where we have y to be equal to A exponential raised to power R1s plus B exponential raised to power R2s, where A and B are what? Are constants. They are constants. So in case 2, for case 2, when R1 and R2 are equal, when we have a repeated root, we have a general solution of this form, where A equals exponential Rs plus B with additional of S exponential Rs. We have case 2 of that form. And for case 3, we have when the roots R is a complex conjugate. Now we have, in a complex number, our answer is always of this form, where we have alpha plus or minus beta what? Beta I. Here is real, while this is what? Imaginary. So when we have a complex conjugate, our general solution will be in this form, where the real will be raised to the exponential. Look at the alpha s. Then we have A, where A is constant, and we have cos beta s plus B sine beta s. So in a situation whereby you have 5 plus 2i, our 5 is the real here, which is alpha. Our 2 is our beta. So our general solution will be changed to what? Instead of writing beta here, we have 2. So we have 2s plus B sine 2s. Our alpha will be what? Our alpha will be 5. So this how to solve problem related to second order differential equation with a constant coefficient. We have 3 cases. When the roots are not equal, we have a situation whereby the roots are equal, and we have a case where we have a complex conjugate. So I'll solve several examples related to this. Then you understand better what this topic is trying to explain to us. So I'll solve an example on second order differential equation, and the example is on the board. When you are solving this type of second order differential equation, the first thing you are going to do, or before I solve this problem, I will need to write it in form of in standard form. So this can be written as our d squared minus 8d plus 15 all bracket y equals 0. So this equation here is also the same thing as this. I just want you to note that. Now, on solving this problem, we convert it to a quadratic equation, and that will give us m squared minus 8m plus 15 equals 0. Now, from our knowledge in secondary school or high school, we can easily solve this quadratic equation. On solving, this will give us m minus 3, m minus 5 all equals 0. So which implies that our m minus 3 equals 0 or m minus 5 equals 0. So m equals 3 or 5. So this is the value of our m. Now, so this is actually the first case that I said earlier, where R1 is not equal to R2. So since R1 is not equal to R2, our y complement will now be given as what? A exponential 3x plus b exponential 5x. So this is our final answer. So this is another example on our second order differential equation of a constant coefficient. So we have this already. So convert it to a quadratic equation. You have m squared minus 6m plus 9 equals 0. So when you solve this, we have m minus 3 all squared equals 0. So in this case, we have m to be equal to 3 twice. So if you look at this second example, it's the same as this case 2, where we have R1 to be equal to R2, all equals to R. So if you have something of this form, our y complement, which is our general solution, will be equal to a plus bs all exponential 3x. Yeah, that's our final. So I want to solve another example on second order differential equation with a constant coefficient. So we have another question on the board. The same procedure. We have m squared plus 4m plus 5 equals 0. So when you solve this, we are going to get a complex value where our m will be equal to minus 2 plus or minus I. So this is what we are going to get as our root. Now, from the cases I gave you earlier, how do we solve this? As I said earlier, I said when you have your root r to be equal to alpha plus or minus beta I said our general solution will be y to be equal to a alpha bracket a cos beta x plus b sine beta s. So we are going to use the same procedure to get our general solution here, where our y now will be equal to, our alpha stands for what? Minus 2. So e raised to power what? Minus 2s, open a bracket, a constant a, cos. Now instead of writing beta s, the coefficient of I here is what? 1. So we have just cos s plus our b sine s. So this is our final answer. So thank you very much. Please, you like, share and comment in order for this to boost my morale. Then I'll give you better ways to solve problems in mathematics. Thank you.